Welcome to section B of chapter 16. So continuing our talk of fluids, we're going to talk just about gases today, and we're going to go through several gas laws. One of my favorite lectures to give, because there's so many demos for this. I've made an entirely separate video for all the demos, because otherwise this one will be just too long. So this is the notes and the words for it. Check out the gas laws demo video though to see all the fun stuff. Okay, so when we think of these gas laws, we have to kind of just remember the states of matter a little bit, okay? Solids, the particles are very condensed and close together. Liquids are starting to spread out and move a little bit more. Gases, they spread out to fill whatever container they're in. They're moving the most with a gas, okay? So I'm in the classroom right now. The gases are going to evenly spread out in the entire classroom, okay? Think of the atmosphere as the container for our huge system on Earth, okay? Any gas has four properties that we can measure. The number of particles, which gets into moles and molar chemistry, and we're not going to go there in this lecture, okay? The three that we're going to focus on are volume, so how much space it's taking up, temperature, obviously what temperature it is, how, the average kinetic energy of those particles, and also the pressure. So when the gas particles are in a container, they're actually bumping into the container. That is pressure, okay? So those particles are exerting that pressure, an outward pressure on whatever container it's in, okay? All right, so the first of our gas laws is called Boyle's law, okay? And so we're gonna talk about volume, temperature, and pressure. Each of these laws relates only two at a time, okay? So Boyle's law is going to talk about pressure and volume, and it's going to assume that temperature is constant, meaning it's not changing, okay? So Boyle's law tells us that when the pressure on a gas increases, the volume decreases. Now this should make perfect sense. So if I have a gas in a confined container and I start squeezing it, it's going to require less room. It's going to condense those particles and they're going to get closer together. Okay. The reverse is also true. When the pressure is decreased, then the volume can increase. Okay. So this is decreasing the pressure. That plunger is moving up. Now these particles have more space and they're going to fill that space. So the volume gets higher. When I push down on this plunger, those particles have less space. And so they're going to have less volume. Okay. This is what's known as an indirect relationship. Okay. Again, temperature is constant. Indirect meaning when pressure goes up, volume goes down. When pressure goes down, volume goes up. So it's an opposite relationship, indirect, okay? This is what happens in when you try to separate buckets. I don't know if you've ever had like two Home Depot buckets and you try to pull them apart. Sometimes it's almost impossible. Because what you're doing, you've trapped some air between those buckets. And as you're pulling them apart, okay, you're decreasing the pressure on them, which lowers the volume inside, okay? It increases the volume, but it gives these particles an opportunity to spread out, okay? So you can kind of think of the pressure inside also decreasing. So now higher pressure outside is going to push those buckets together, okay? Weather balloons is another good example, okay? A weather balloon is filled with a certain amount of gas, takes up a certain amount of volume, okay? As the weather balloon goes up in the atmosphere, remember, air pressure decreases as altitude increases. So as it's going up into the atmosphere, the pressure on the balloon is decreasing. And so the weather balloon can actually expand. The volume will increase, and it'll keep doing that until eventually it pops. And then that's what brings the weather balloon and all its instruments back down to Earth. People will do this with like GoPro videos, and they can retrieve the footage. They know that it's going to pop eventually because the balloon will only stretch so far and then it comes back to Earth. All right, Charles' law is now going to relate volume and temperature together and kind of ignore pressure. So pressure is constant with this, okay? So Charles' law tells us that when the temperature of a gas goes up, the volume increases, okay? Now this should make sense because when you increase the temperature of a gas, that means they're moving more, okay? And so they're going to be stretching their container. They're going to be bumping into that container more. And if the volume is stretchable, if the volume can change, it's actually going to cause it to expand. The reverse is also true. If you decrease the temperature, those particles are going to get closer together and not require as much space. The volume will go down, okay? Again, faster moving particles will spread out more, slower moving get closer. If they spread out more, that's more volume. If they get closer, it's less volume, okay? This is a direct relationship, meaning that they both move in the same direction. Pressure is constant. Both temperature and volume will increase together or decrease together. Direct relationship, okay? An example are like playground balls. If it's really cold, so let's say you take a playground ball outside, it's nice and sunny, and it's a nice, full ball, okay? If you leave it out overnight, as it gets really cold, the decrease in temperature is going to cause those particles to come together, and the ball will actually feel less inflated. None of the air has actually escaped. It's just more condensed, so less volume. Balloons, same idea, okay? Balloons will change their volume because a balloon can stretch with temperature. If you stick a balloon in the freezer, it's actually going to shrink a little bit, okay? If you stick it out in the sun, it will increase and possibly even pop, okay? All right, third one is now going to relate temperature and pressure together. And this one's a little, I don't know, controversial is too strong of a word. It's named different things. It was known as Gay-Lussac's law, and that is what the book refers to it to. Recently, it's been known as Amonton's law, and there's some contention on who should actually get the credit for coming up with this. Okay. In any case, what it states is that when the temperature goes up, so does the pressure. Okay, so this is very similar to the volume one. Now, what I've got is a gas in a container that can't change. So the volume is constant. So like glass or metal containers, okay? If I increase the temperature of that gas, the particles are going to be moving more and they're going to be spreading out. And so they're going to be hitting the container, which won't change its shape or volume. So that means there's going to be more pressure on that container because they're hitting it more, okay? Higher temperature again, faster motion, so more outward force, okay? Higher pressure. This is also a direct relationship. Volume's constant, it's not changing. Both temperature and pressure will go up together or decrease together, okay? And our example are tires, which you can make the argument that tires can actually change their volume because they're rubber, but it's difficult for them to do that. A better example would be like propane canisters or like a metal canister, an oxygen tank, something like that. Something very rigid, okay? This is why it's not safe to put these sealed canisters in a fire because you're going to increase the temperature, which will increase the pressure, and they'll eventually blow up and really, really can be very dangerous, okay? If something's left out in the cold, the pressure will decrease. The opposite is also true. So we could put all these three things together in something known as the ideal gas law, okay? So sometimes the pressure, the temperature, and the volume are all interacting at the same time. This ideal gas law is also known as the combined gas law because it combines all three. This is the common way it's written. You've got pressure and volume on one side of the equal side. You've got N, which is the number of particles. Again, we're not going to really talk about that much. You've got R, which is a constant. It's known as the gas constant. We're also not going to talk about that very much. And then T is temperature, okay? If you look on page 385 in the book, though, it talks about the fact that you can rearrange this equation and make it a ratio of the pressure and volume to temperature, and that's actually going to be equal to that gas constant, okay? So it takes three things we've talked about and relates it to that gas constant, okay? If you look at this equation, though, you can kind of see why the pressure and volume are an indirect relationship. If pressure goes up, volume has to go down to keep this as a balanced equation, okay? If temperature goes up, pressure also has to go up because they're on opposite sides of the equal sign, okay? Same thing with volume, okay? So if temperature goes down, volume has to go down, opposite sides of the equal sign, okay? So I want you to get a popsicle stick, or I'll give you one of these in class, and you can have a little trick here to kind of help you remember what happens with these things, okay, with these three laws. Since one of these measurements is constant, if you place your finger over the thing that's constant, okay, so if temperature is constant, what happens when volume increases? When volume increases, pressure goes down. What happens when pressure increases? Volume goes down. Pretty fun, right? Okay, so now pressure is going to be constant. What happens when temperature goes up? Volume went up also. What happens when temperature goes down? Volume goes down. And then the same is true when volume is constant. If the pressure goes up, temperature goes up, temperature goes down, pressure goes down. So a little trick to help you remember the relationships between those things. Okay. And again, check out the gas law demos because it'll really kind of help you visualize what's actually happening with all these laws. Okay. See you later.